Hi, this is Ms. Fitzmaurice, and this video is Parallel and Series Circuits, Part 3. So in this video, we're finally going to get to Kirchhoff's loop rule, then we're going to talk about Kirchhoff's junction rule, and then finally we're going to do some example circuits where you're going to test your knowledge and try to figure out the voltage drop and the current through specific resistors. So in Kirchhoff's loop rule, we have to think about the idea of conservation of energy. And I'll illustrate this in a non-circuit way. So imagine that you have a floor and a book is sitting on the floor. Okay, then you pick the book up and you put the book ultimately back to its same place. It doesn't matter what you do with that book. You could bring it over to the right, you could bring it to the left, up, down, whatever. Okay, it started and it ended in the same place. So its total change in energy is going to be zero. Okay, at the beginning it's just sitting there, it has no potential energy, and no matter what you do with it, by the end, it still has no potential energy. It's not moving. It has no energy. Okay, that would be just as true if you had a book that was sitting on a table. Okay, so like, imagine that your book starts right here instead, then you bring it down to the ground, and you bring it back up. You might bring it to the left or the right, as long as it ends up in the same place and it has the same motion at the end. Its change in energy is zero. The same thing is true for electrons going around the circuit in a battery. Okay. If they start at the battery, go through the circuit, and they end back up at the battery, no matter what path they take, their potential energy change should be zero by the time they make it all the way around the loop. And because potential energy, or because voltage is potential energy per unit charge, the same should be true for the voltage around the loop. Okay, so Kirchhoff's loop rule is just a conservation of energy, and all it says is that if you add up the voltage around a whole closed loop, you should get zero. Or you add up the change in voltage around a closed loop, again, you should get zero. Okay. And that should be true no matter what loop you go around. So you could go around this first loop I drew, and every time you lose a resistor, or you go through a resistor, you lose voltage. But then when you get back to the battery, you gain it all back again. But it's also true if you think about the voltage around this loop. Okay? And the way you can think about that is, you know that this loop, it's connected on two ends, and whatever the voltage drop in this direction is, say this is VA and this is VB, going the other direction you need to have the same voltage drop. So if you're going this way, you would have the same voltage drop. But if you go around in a closed loop, you're going back the other way, and so you're kind of adding the negative of your original change. Okay, and that will give you zero. Now the question is, how do you represent this mathematically? And to represent this mathematically is actually pretty easy. Okay, so for any loop that you can draw, and I'm going to look at this loop right here, okay, this orange loop, as long as you've named your resistors, or you know something about your resistors, I'm going to name this resistor A, resistor B, and resistor C, we can write out or Kirchhoff's loop, okay, we know that at the beginning we have our battery. So I always start at the battery if my loop goes through a battery. And we have the whole voltage of the battery. So whatever that is, you know, whether it's 15 volts, 9 volts, 1.5 volts, that's the first thing we add. And then as we go through the loop, we add the voltage drop across every resistor. So we have V battery plus VA plus VB plus, because we've gone through resistor A and B, plus VC equals 0. But I have other resistors in my battery, or in my circuit. So I'm going to name these guys D and E, and it will be equally true that V battery plus, and I'm going to represent this with a gray loop because I haven't done gray yet. But if I go through the battery and then I go through D, and then I go through E, and then I come back to the battery, that's a different loop. So I would write for that loop V battery plus VD plus VE equals 0. And I could set up 2 more loops, at least. There are actually a lot of loops I can do, but I'll draw this curly-cued one. Okay, I could go through D and then go through C, and so I could set up the loop V battery plus VD plus VC equals 0. And I could keep doing this, and you might be saying, well, why would I want to do that? And the answer is, if you want to know the current through one resistor, or the voltage drop across a particular resistor, one of these equations won't be enough for you to solve. Okay, in the same way that when you were in Algebra 2, if you had 3x plus 4y minus 5z equals 0, you wouldn't be able to solve for x or for y or for z. But if you had 3 more equations with x and y and z, so, you know, it doesn't matter what those are, 2x minus 4z equals 0, x plus y minus z equals 0. Then you could use these 3 equations together, or this system of equations, to solve for your voltage. Alright, so Kirchhoff's loop rule was about conservation of energy. Kirchhoff's junction rule is about conservation of a different type. It's about conservation of charge. And so hopefully you learned in chemistry that charge, as in the charge on protons and electrons, cannot be created or destroyed. No matter what you do, the total amount will stay the same. So if you have a circuit and you have electrons going through this circuit, then no matter what you do, the number of electrons going through at a certain time is going to stay constant. And the idea is, whatever the current is over here, that's the number of electrons per second, that's going to stay constant all the way until our circuit kind of starts to branch off. Okay, once our circuit branches off, half, or not exactly half, but some fraction of the electrons go one way, and then one fraction of the electrons go the other way. Eventually, those electrons are going to come and join back together, and the final current will be the same as the initial current. Okay, so The idea behind Kirchhoff's junction rule is that whenever you come to a junction in your circuit, the total current going into your circuit has to be equal to the total current going out of your circuit. And usually we label currents with just numbers, so I would label this I1, I2, and I3. So if I was writing Kirchhoff's junction rule for this green junction, a junction is just anywhere that wires are separating or coming together, I would just write the total current in, which in this case is I1, is equal to the total current out, and that's I2 plus I3. Okay, and this seems easy enough. The question is, how can this, in combination with our voltage equations, help us solve for things? Because, you know, in some of them we have only voltage, in some of them we have only current. And the trick is that each of these voltage drops, we know that in general, voltage equals IR. And so for each of these voltage drops, it's a drop, so it's going to be negative I times R. And we'll be able to put the current I and the resistance R to each one of these voltages, and then we'll use both the voltage loop rule and the current junction rule in our system of equations to solve for currents and voltages. Okay, so now it's time, now that we know both the junction loop rule and the loop rule, to try to apply them. So in this case we have a circuit, we have a 15-volt battery and two 200 ohm resistors in parallel with each other, and they are in series with a 50 ohm resistor. And what we want to do is we want to try to use both the loop rule and the junction rule to find the current through each resistor. And I'm going to label my resistors A, B, and C. And I also want the current through each resistor. I'm going to start by using the loop rule. And I want you to pause this video and just draw the two loops that you think will be most valuable as we go through in solving this. So now that you've done that for yourself, I'm going to draw them for you. Okay, I think this is our first loop. We go through the battery, then through resistor A, and back to the battery. And then secondly, we're going to start from the battery, go through resistor B, go through C, and go back to the battery. And for both of these, I can use the loop rule. Remember that it's the total change in voltage around a closed loop equals 0. So I'm starting out over here at the battery. Okay, the battery gives me 15 volts, so I gain volts from the battery. Okay, then I go through resistor A and I lose volts. Okay, so minus VA. I go through resistor C and I'm losing volts, so I have minus VC, and I set it equal to 0 because that's the last thing I see before I run back to the battery. Same thing with resistor B. I have 15 minus VB minus VC equals 0. Or I could say plus, but I know I'm losing voltage through each of these, so I'm adding a negative number, which is the same thing as subtracting. Those are my loop rules. If I wanted to, because I know my junction rule is going to give me currents, I can say this is really 15 minus, I know VA is IA times RA, which is 200, minus IC VC, RC, and RC is 50 equals 0. I can do the same thing with VB. I have 15 minus IB, RB, which is 200, minus IC times 50 equals 0. Okay, so those are my two loops. I really only have one junction here, only one place, either here or here, where my currents are coming together or falling apart. And I want to use the second one because I have the current through C. Okay, your brain should be telling you whatever the current is through C, so we'll call it IC, is the same current as comes out of the battery because there's no split between C and the battery. Okay, but we'll use this bottom one down here. So our junction rule tells us that IA plus IB equals IC. Now I have three equations, 1, 2, 3, and 3 unknowns. And much like you did with systems of equations in Algebra 2, I can use these three equations to find my three currents, and once I have my three currents, I can easily find my voltages. So what I'm going to do is I'm going to label my equations 1, 2, and 3, and I'm going to write them again on the next page, and we will solve them. Alright, so here are my three equations. Notice that 1 and 2 are exactly the same except for IA and IB. And what that tells me is that it might be useful to subtract those two equations. So I'm going to do that. I'm going to do equation 1 minus equation 2. And when I do that, I get 15 minus 15. So I'm looking only at the right-hand side. 15 minus 15 is 0. Okay. Minus 200 IA minus negative 200 IB is not quite 0. But then I'll have minus 50 minus minus 50, and that's also equals 0. Okay, so all the things that aren't the same, or that are the same, will cancel out. And then on the right-hand side of my equation, over here, I just have 0 minus 0, and that gives me 0. Okay, I'm going to simplify this by dividing by 200. Okay, I have a 200 in each term, so I'm going to get rid of that. Now I need to make a little bit of sense of my negative signs. So I have negative IA minus minus IB, so plus IB equals 0. And what that tells me is that IA equals IB. And I'm going to take this piece of information and I'm going to substitute it in. I'm going to call this 1 prime. Okay, and I'm going to sub 1 prime into my third equation. Okay, so I'm taking this IA equals IB and I'm just going to replace IA with IB. Okay, so 3 becomes IA, or IB, because I'm replacing IA, plus IB equals IC. Okay, and I can simplify that to IB equals IC. And now I can go ahead and I can put that back into equation 2. So I'm going to call this 3 prime, and I'm going to substitute 3 prime into equation 2. And when I do that, I get 15 minus 200 IB minus 50 times 2 IC, times 2 IB, because we're replacing IC with 2 IB, equals 0. Okay, then we can go ahead and actually solve for IB. So I'm going to write that on the next page. I have 15 minus 200 IB minus 50 times 2 IB equals 0. 50 times 2 is, of course, 100, so I have 15 minus 300 IB equals 0. Okay, 15 equals 300 IB. I divide both sides by 300, and I end up with IB is equal to 1/20th, which is 0.05 amps. Okay, so now I have one of my currents. But I already know, because I wrote it down before, that IA equals IB. So then I know IA equals 0.05 amps. And I know that IC is 2 times IB. So I know that IC is equal to 0.10 amps. Okay, just twice as big. Okay, so now I have all my currents. If I want my voltages, I can use V equals IR for each. So VA will be IA RA. And we know that IA is 0.05 and RA is 200. So I should get 200 times 0.05, and I get 10 volts. And for VB, instinct tells me that I should get the same number. I get IA, or IB, RB, and again, I have the same numbers. I have 200 times 0.05, and that's 10 volts. And for VC, I have IC, RC, and that's going to be 0.1 times 50, which is equal to 5 volts. Okay, so now through this whole process, I was able to find all of my currents and all of my voltages.